Hello and welcome back to the machine learning video series. Up till now, we have discussed the general steps in machine learning. However, we have not yet seen how the system actually learns from the data. Of course, unlike humans, the model cannot interpret or learn from the data by itself. Let us consider regression problems. We have discussed that regression problems fall under supervised learning. Our data will have some features corresponding to a continuous output distribution. A popular example is house prices depending on the number of bedrooms, total area, etc., or the salary of an employee depending on experience, qualifications, etc. Regression problems are easier to deal with as the accuracy of the output can be judged easily. If the output is close to the actual label, the output has less loss and is therefore more accurate. If the actual and predicted label has wide difference, the model is of course not performing very well and has low accuracy. Now, linear regression is the simplest example of a regression problem. Let's consider an example where we have only one feature corresponding to the output label. It can be expressed in the form of an equation y equal to wx plus b, where y is the output label and x is the feature. W and b are to be modified such that for an input x, the value wx plus b comes out to be close to actual label in the dataset. Now, consider these scattered points. Intuitively, if we draw a line through these points such that it passes through all these points from a small distance, we can say that for any new input x0, the output label will definitely be w into x0 plus b. Hence, we only have to figure out w and b to be able to predict the label of any unseen data point. Let us analyze three lines through the given points. Which line do you think will give a better output? As humans, it is easy for us to judge that the third line is the best one. But how do we tell a computer that it is the best line? By observation, the best line is expected to have minimum distance from all the points in the data. It does not have to touch all the points, but it should be near most of the points. Now, we need to define an error function so that our model gets an idea of how correct or incorrect its predictions are. Here's how it is being done. In regression, the simplest idea of closeness of the line from the points is the vertical distance between the actual point and the point where the line crosses that value of x. This vertical distance is nothing but the difference between the predicted and actual value. Hence, for a data point x0, y0, the error is mod of w times x plus b minus y. The error is squared to remove the negative sign and to increase proportional penalty. An important thing to note is that this error across the complete data set is to be minimized and not just about a single data point. It does not make sense to minimize error about one point, right? Hence, the total cost is the sum difference between all pairs of predicted points and actual points, and the objective is to minimize this formula. Finally, we will use the given formula as our cost function. It is nothing more than what we have discussed. The sigma just signifies that the cost is calculated for each point in the data frame and the sum is calculated. The sum is then divided by 2m. For example, say if the cost at every point in our data set is very small, but there are a lot of points in our data set. So, when we add the cost about each point to get the total cost will come out to be large. But actually the accuracy would not be very bad. To avoid this situation and to get a more accurate idea of the loss across whole data set, we have to divide the total cost by m, that is the number of samples in our data set. Take the example of two data sets, one of which has only 4 samples and the other one has 14 samples. Say we train two different models and their respective predictions are given in the third column of the data frame. In the smaller data frame, we can see that the model prediction is always 0, irrespective of the input x. This is actually a very bad model and must have high cost. Now, if we calculate its cost without dividing it by the number of samples, the cost comes out to be 14, which is actually pretty high. Alright, now look at the other data frame which has 14 samples. we can see that the predicted value is always 1 more than the actual value. This is not that bad. It is significantly better than the previous predictions. But if we calculate its cost function without dividing by the number of samples, the value turns out to be 14. Well, this doesn't seem to be favorable. The previous model was much worse, but the cost comes out to be the same value. Now let's divide the cost function by the number of samples. The cost of first data frame becomes 14 by 4, that is 3.5. The cost of the second data frame will become 14 by 14, that is 1. Now we can at least figure out that the second model was better than the first one. That is why we prefer to divide the cost by the number of samples. It gives a more accurate picture of model performance. There is 2 multiplied by m in the denominator because of no particular reason. It is just a common practice to multiply m by 2 before dividing. It does not affect our model in any drastic manner. This was a cost function used to reduce errors in regression problems. See you in the next video. Thank you.